In this video, we're going to talk about pTests. Now, we've already set up all the machinery for pTests, so I'm going to review a little bit of that machinery, and then we're going to talk about the tests themselves. So first, we have null and alternative hypotheses. So we often present a hypothesis to be tested with data. And the null hypothesis, H0, represents a skeptical perspective or claim to be tested. The alternative hypothesis, HA, represents an alternative claim under consideration. It's often represented by a range of possible parameter values. Now, a skeptic will not reject the null hypothesis unless the evidence in favor of the alternative hypothesis is so strong that she rejects H0 or H0 in favor of HA. So, we've talked about this example before. A poll by the National Sleep Foundation found that college students average about 7 hours of sleep per night. Researchers are interested in showing that students at their school sleep longer than 7 hours on average, and they would like to demonstrate this with a sample of students. So the null hypothesis in this case is that students average 7 hours per night, or H0 equals 7, or even H0 is less than or equal to 7. The alternative hypothesis is that students average more than 7 hours per night, or HA is bigger than 7. Okay, we have two types of errors which we've talked about. A type 1 error is an error where you reject the null hypothesis, but it is true. And a type 2 error is an error where you do not reject the null hypothesis, but it is not true. So, go back to the sleep example. The null hypothesis is that students average 7 hours per night, or H0 equals 7. The alternative hypothesis is that students average more than 7 hours per night, or HA is bigger than 7. A type 1 error is that we accept that the students average more than 7 hours per night, but they only average 7. We reject the null hypothesis, but it's true. A type 2 error is that we accept that students average only 7 hours per night, but they average more. So again, we accept the null hypothesis, but we should have rejected it. We now talk about the test statistic. So we want to know how confident we are. We would like to be able to say by how much we rejected the null hypothesis. Did we barely reject it? Or not only we rejected it, but it wasn't even plausible. So in order to evaluate if the observed sample mean is unusual for the hypothesized sampling distribution, we determine how many standard errors away from H0 it is. And this is called the test statistic. So the test statistic is the z-score of the sample distribution mean in the hypothesized sampling distribution. So the test statistic is the sample mean minus H0 divided by the standard error. So, go back to our sleep example. The college conducted a study where they asked 110 students how much sleep they averaged per night. The students averaged 7.42 hours, and the standard deviation of their result of this survey was 1.75 hours. Now we can calculate the standard error. That's 1.75 divided by square root of 10, or 0.1669. If we assume that these are a simple random sample of students and 110 is less than 10% of the population, then we can assume they're independent. Given we have a large sample size, we can ignore skewness. Thus, we can assume that the sampling distribution is a normal distribution with mean 7 and standard deviation 0.1669. Again, this mean is the null hypothesis. Again, this is what our sampling distribution looks like. In blue, we have plus or minus 1 standard deviation, so 68% of the distribution is in that. 2 standard deviations, that's about 95% of the distribution, again in orange, and 3 standard deviations is in green. Now, the hypothesized sampling distribution has mean 7, standard error 0.166 should be 9. The sample has mean 7.42, and so we can calculate the test statistic. Sample mean minus H0 divided by standard error, or 7.42 minus 7 divided by 0.1669. That's 2.52. So the sample mean is 2.5 standard deviations away from the hypothesized mean. Now it's possible, of course, to choose a sample that has a mean that far from the from H naught, but it's not very likely. 2.5 standard deviations is pretty far into the tail of the distribution. So let's talk about p-tests. So we're going to talk about one-sided p-tests. There are also two-sided p-tests, but we're not going to use those in this class. Okay, when you're interested in checking for an increase or a decrease, but not both, then we can use a one-sided test. If you're interested in any difference from the null hypothesis value for the mean, then the test should be two-sided. So a one-sided test, we want to know whether the test statistic favors the null hypothesis over the alternative hypothesis with a significance level alpha. So assume that the null hypothesis is that the true mean is mu, and the alternative hypothesis is that the true mean is greater than mu. The sample has distribution, has a mean, x bar we'll call it, and a standard deviation sigma, and sample size n. So the distributions of samples should have mean mu, that's the null hypothesis mean, and standard deviation equal to the standard error, sigma over square root of n. Again, that's under certain conditions. The test statistic is the sample mean minus the null hypothesis mean divided by the test statistic, sigma over square root of n. Now, the area in orange in this graph represents the chance of selecting a sample from the actual distribution or from this null hypothesis distribution with mean above the sample distribution mean. If this is small, then we reject the null hypothesis in favor of the alternative hypothesis that the actual mean is greater than the null hypothesis. On the other hand, if it's large, we can't reject the null hypothesis in favor of the alternative hypothesis. This doesn't mean that we accept the null hypothesis, just that we can't tell whether the null hypothesis is true or the alternative hypothesis is true. If the alternative hypothesis is that the mean is less than the null hypothesis mean, then the area is on the left. So the significance level alpha is often selected to be 0.05, corresponding to a 95% confidence that the conclusion is correct. A smaller significance level, so say 0.01, reduces the chance of a type 1 error and increases the chance of a type 2 error. Right? So type 1 error, again, our table here shows it. Type 1 error is where the reality is the null hypothesis is true and we reject it. Type 2 error is a reality where the alternative hypothesis is true and we don't reject the null hypothesis. So again, smaller significance level reduces the chance of a type 1 error and increases the chance of a type 2 error. A larger significance level increases the chance of a type 1 error but decreases the chance of a type 2 error. So the p-value is the probability of observing data at least as favorable to the alternative hypothesis as the current data set if the null hypothesis is true. We typically use a summary statistic of the data, for example, the sample mean, to help compute the p-value and evaluate the hypothesis. In Excel, the p-value is norm.s.dist of the test statistic or 1 minus norm.s.dist of the test statistic. Again, it's the area in the distribution that's either below in the first case or above in the second case. So we go back to our sleep example. The hypothesized sampling distribution has mean 7, standard error 0.1669. The sample has mean 7.42. The test statistic is 2.52. The p-value is, again, this is above, so we use 1 minus norm.s.dist of 2.52, and we get 0.006, which is fairly small. If we want a 0.05 significance level, or 95% confidence that our conclusion is correct, then we would reject the null hypothesis in favor of the alternative hypothesis that students sleep more than 7 hours a night. Right? And that's because our p-value is smaller than the significance level. The smaller the p-value, the stronger the data favors the alternative hypothesis over the null hypothesis. A small p-value, again, less than 0.05, is often chosen, corresponds to sufficient evidence to reject the null hypothesis in favor of the alternative hypothesis. If the null hypothesis is true, how often should the p-value be less than 0.05? About 5% of the time. All right, one last little comment here about the significance level. Sorry, the traditional level for significance testing is 0.05 or 5%. And we can adjust that depending on what we're doing, depending on what we're interested in. Now, there's a video here on why, if you're interested, but we'll just talk about a couple of examples, right? Type 1 and type 2 errors. This is how we choose our 0.05. If type 1 errors are really bad, if there are significantly bad consequences of type 1 errors, then we want to choose a smaller significance level. If type 2 errors are significantly bad, right, so something really bad comes out of type 2 errors, then we want to choose a higher significance level. So we need to look at what we're testing, H0 and HA, and we need to think about, are we better off with type 1 errors or type 2 errors? And if we're better off with one or the other, in a significant way, we might want to move this significance level from 0.05. So a couple of examples to keep in mind. So let's say the consequences of a guilty verdict is the death penalty. The type 1 error, in this case, is convicting an innocent person. That has a pretty significant penalty. So we might want to avoid these types of errors by decreasing the significance level at which we reject the null hypothesis, innocent, and accept the alternative hypothesis, guilty. So maybe instead of 0.05, we use 0.01. What about a test for a particularly deadly form of cancer where the cancer is treatable if discovered and the treatment is not terrible if you don't have the cancer? Well, in that case, you might accept more type 2 errors where you diagnose the patient as having the cancer even if they do not, because we don't want to find ourselves in a position where we have lots and lots of patients for whom we have said they don't have the cancer but actually do.